All right, I'm going to send you guys the updated document of the class. Now, just follow me step by step, and we're going to work on confidence intervals for difference between two proportions. The difference, two proportions might differ from each other. Look at this example. Look at this example. Suppose 84% of a simple random sample of 125 nurses working between the 7 a.m. and 3 p.m. shift in the city hospital express positive job satisfaction. You have a proportion. You have a proportion of these nurses who are working in the day shift. 84% of them are satisfied with the job, but you have another sample. This sample of nurses work like 11 p.m. to 7 a.m. That's an evening shift. And only 27% of these people have positive job satisfaction. And we want the 90% confidence interval for the difference. Here, we are concerned with the difference between the two proportions, the two proportions of satisfied workers. And the two proportions, well, we know from the samples. For one sample, we have 125 people. That's for the day shift. For the night shift, we have a sample of 150 nurses. And that's the information we have. We measure 150 people from the night shift and 125 people from the day shift. And we want the 90% confidence interval. For the difference between the two populations, we are concerned about the populations of night shift and day shift. Here we have some parameters. Parameters refer to population. These are different from statistics. Statistics describe your sample, but parameters are about population. P1, proportion 1 is a proportion of the population here. This is really important. It's different from your sample. We're not talking about the sample of 125 nurses. We are talking about the all nurses who work the day shift. And then proportion 2, P2 is a proportion of the population of nurses working on the night shift that are positively satisfied with their jobs. These are the two proportions we are concerned with. And we need to do some checking. Well, we're going to use a normal distribution. Every time you see the confidence interval, 90% confidence interval, you know you're going to work with a normal distribution. The normal distribution, the normal curve will give you the proportions of the distributions, the probability density curve. That is what you are going to use. To use this curve in a legitimate way, you will need to check some conditions. First of all, you check the n times p. The n is the number of people in your sample. In the first sample, this is day shift nurses, 125. The proportion, the p, the satisfied nurses proportions 84%. And the result N1 times P1 is 105. You want this number to be at least 10, equal to larger than 10. And then you want to check n times 1 minus p. This is also called the Q, the complement of the proportion. You have 125 times 1 minus 0.86. That's 0.16, sorry, 1 minus 0.84. That's 0.16, and you get 20. That is larger than 10. And then you check the second sample. N is 120, 150. You got 150 nurses from the night shift. And the proportion, the satisfied proportion 0.72 is larger than 10. And then you have 150 times 0.28 is larger than 10. That's good, sounds good. And you also want to make sure that your sample size is smaller than 10% of the population. Now, it is reasonable to assume that your samples are 10% or less than the population. And then the next step is that you get the confidence interval. What do you have in the confidence interval? You have the confidence level. We know that. We want the confidence level to be 90% confident. And then you need the estimate. You need the estimate of a difference between the two proportions. What's the difference between the proportions of satisfied nurses on the day shift versus on the night shift? Are there more nurses who feel satisfied with their job on the day shift than on the night shift? Sounds like there should be. Working the night shifts really hard. Staying up all night, that's really hard on your body, on your health. So we want to estimate the difference in proportions. And also we want a margin of errors. We want a upper boundary, lower boundary for the margins of error. And let's see. We are using the samples as estimates. You have, for sample 1, 125 people. Sample 2, 150 people. From each sample, you have measured a proportion. For the first sample day shift, your proportion is 84%. 84% of them feel pretty good about their job. And from the second sample, 150 people, these are night shifts. Night shift nurses, only 72% of them are satisfied with their jobs. And then the difference, what's the difference between these two proportions? You have observed the difference. Observe means these are the samples, sample statistics. 84% minus 72%. The difference is 12%. There is a 12% difference between these two samples. And what is your estimate of the population? Your population are all the nurses in the hospital, all the nurses on the day shift, and all the nurses on the night shift. And this you are going to estimate. The estimate for the population you can get is the same as the sample. Your estimate for the proportions between the two populations in the whole hospital in the entire hospital is the same as here, 0.12, 12%. That is your best guess. We don't have any new information. We don't have any better information than this. If you're observing that there's a 12% difference between the two samples, night shift, day shift nurses, you have actually measured, this is your best educated guess on the difference between the two populations in the whole hospital. And we want to get a margin of error. The margin of error is very much related with your confidence level. And we are looking for a confidence level of 90%, 90%. What does that mean? That means you need to look at the normal curve, the normal distribution. See if I have a normal curve here. Yeah, you need to have a normal curve and you want 90% of the curve between the two boundaries, lower boundary and upper boundary. I'm just using this normal curve as a demo. This is not the right normal curve to use because the numbers are wrong. So you want 90% to be in the middle, covered by your two boundaries, z-score boundaries. And you want a z-score boundary, positive and negative, to give you 90%. 90% right in the middle. So if you have a 90% around the mean, you have a mean to z of what percent? 90% divided by 2. Let me get a calculator. Here. 90% divided by 2, that should be a 45%. So I'm gonna get I need the normal curve, normal table. Where is that? The normal table of a standard normal distribution. Yeah, 45% on each side. Let's see, 45% on each side. Where do I have that? 46, 44. Here, 1.6 something. 45 seems to be here. This one is close. 1.65 seems to be 1.65 is good. The closest one I can get. 45%, 1.65. .65 standard deviations above the mean and below the mean. Here, let me go back. If you want to be more precise, if you want to go to a 3 decimal points, if you have a 3 decimal point z distribution table, or if you use a calculator, and then you can find the 1.645. 1.645 standard deviations above the mean and below the mean. This will give you a 90% of the normal distribution. So your critical z-scores are positive 1.645 and negative 1.645. So between these two z-scores, you will have 90% of the population. And then these two z-scores will give you the margin of error. You want to convert these two z-scores into a raw score, of proportions, the differences between the two proportions. So you have a z-score and you have the mean, the average difference in proportions. What you are missing is the standard deviation. You want 1.645 standard deviations above the mean or below the mean. You have the mean, it's 12% difference on average. There's 12% difference between the night shift and day shift in satisfaction. And you just need the standard deviation. You need the standard deviation for the distribution of differences in proportion between the two samples. So here's how you get it. We call it a standard error when we try to estimate the standard deviation. SE, that's a standard error. A standard error or estimated standard deviation between the two proportions. Proportion 1 minus proportion 2, you get it this way. The square root sign shows the standard deviation. This is the square root of the variance. And the proportion, difference in proportion between the two samples, that is, this is P. This is a day shift nurse. 84% satisfied, and then 1 minus 84%, 16%. 16% are the complement. They are the 16%. And you divide it by the number of people in the sample size, 125. And then you add, when you are getting the standard deviation for differences, you add. When you are trying to get a standard deviation for the sum, you also add. It doesn't matter whether you are getting the difference or the sum. And this is coming from the second sample, sample 2. For sample 2, the proportion of satisfied nurses is 72%. And you time it with the complement, the other, the 1 minus 72%, that's 28%. The sample size 150, you divide it by 150. And then you do the math, that's 0.0492. This is a standard deviation, estimated standard deviation. And it's also called a standard error. And now you have the standard deviations. So you can get a margin of error. The mean is 12%. 12%. The difference between the 84% and 72%. And the margin of error is 1.645 times the standard deviation, above the mean or below the mean. You get the raw score. You have the confidence level 90%, and you have the estimated difference between the two proportions, 12%. And the margin of error is like 8.1%, 0.081, that's 8.1% margin of error. And then how you write the conclusions, you can write the conclusions in context. You are 90% confident that the true proportion of satisfied nurses, the day shift versus night shift is between 0.039 versus 0.209, higher than the true proportion of nurses in the night shift. Yeah. So you're estimating the difference between the two shifts. The average difference is 12%. The margins of error is on the lower end 3.9%. On the higher end is 20.1%. That is a confidence interval. Look at this one. A grocery store manager notes that in a simple random, you always get a simple random sample. Sample size 85 people, n equals to 85. These people are going through the express checkout. Only 10 paid with checks. Well, how many people pay with checks? Very few people would pay with checks nowadays. On the other hand, you have another sample, another simple random sample, 92 customers passing through the regular line, 37 still pay with checks. That's a really high proportion. And we want a 95% confidence interval. 95, every time you see this 95% confidence interval, you think about a normal curve, a normal distribution. And you think about the proportions on the normal distribution. 95%, that's in the middle. Between the two parts, you have to divide by 2. And you want the difference between the proportions of customers going through the two different lines who use checks. Confidence interval. You have 2 proportions. Proportion 1, that is a proportion of the population of people. Now you are shifting from sample to population. Your sample is different from the population, a small part of the population. You are having a not really large sample, 85, sample 1, 92 people, sample 2. The proportion 1 is the proportion of people going through the express one, the faster line, who pay with checks. Proportion 2 is a proportion of the population of people going through the regular checkout line who pay with checks. And your observation is pretty obvious. The fast line people, only 10 pay with checks. The regular line, out of 92 people, 37 pay with checks. And you want to get the confidence interval, 95%. Before you do anything with a 95% confidence interval, you need to check the assumptions. You need to check the assumptions and to make sure that you are okay to use a normal distribution for the proportions. See here, where are all my checks? Let's check. N1, the first population, the first samples, N1 is 85, N2 is 92. So what do you want to check? You want to check N1 times proportion 1. What is N1? N1 is 85. Let me get rid of these ones. So N1 is times P1. What is N1? 85 times, let's see, 0.118. 0.118, is that larger or at least equal to 1085 times 0.11? That is 10. Yeah, it is equal to 10. It's okay. It's on the boundary, on the border, although it's not really good. N1 times, so here's N1 times P proportion 1. This should be estimated because it's a sample. And N1 minus P with a hat. Where's my Hassan? 1. That is N1 still 85. That's a 75. So altogether you have 85. And 10 of them paid with checks. 75 paid with some other ways like credit cards. N2 times P predicted 2, that's 37. These are the sample 2. Altogether you have 92 people, and of these 92 people, 37 paid with checks. N2 times 1 minus proportion of 2, that's a complement. 55 paid with some other means in this second sample. They're all at least 10, although this one is kind of on the border. 10, that's okay. And also, we're given independent simple random samples. So simple random samples are really important condition. Also, the 10% rule is satisfied. 10% rule means that each sample is less than 10% of the total population. You can pretty safely assume that 85 is less than 10% of all the shoppers who pay through the fast lane, and this 92 is less than 10% of all the shoppers who are going to pay through the regular checkout. 10% rule satisfied. And then how would you get the confidence interval? Get the confidence interval. First, you get the mean, the estimate. Your observation. You're observing the fast checkout out of 85 people, 10 of them paid with check. That proportion is 0.118. And the other line, the regular checkout out of 95, 37 paid with checks. That's like a 40%. And you see the difference. The difference is pretty big. The difference is like a negative 0.284, 28.4%. So the fast line is 28.4% less likely to pay with checks. And now you need to find a critical z value, the z-score. Now you are using the normal distribution. You are using the normal distribution to get the proportion. You want 95% on the normal curve. 95% on each side. What do you have? 0. So if you get the calculator here, 0.0 5 divided by 2, 47.5%, 47.5% on each side. Again, you go to the z table, 47.5, 47, so you look for 47, 47, that's overshot. Here, some got to be 1.9, you start 1.9, 1.9, 47.5, oh here, 47.5, this guy, this cell give you 47.5 standard deviations above the mean. And that's 1.96, 1.96, 1.96 standard deviations above the mean, and 1.96 standard deviation below the mean. Between these two z-scores, you have 95% of the population. You got the z-score cutoff points. Now what do you need? You need the standard deviation. Your margin of errors is 1.9 standard deviations above the mean or below the mean. So you know the mean, you know the estimate, that's a 28.4. That's the difference between the two samples. This is your estimated population difference between the two lines, between the proportion people use tags in the fast line and in the regular checkout. You know the z-score. Now you need the standard deviation. You need the standard deviation. You don't have it. You don't have the standard deviation of the population. What do you need to do? You need to estimate. When you are estimating, you have the standard error of the mean. Standard error. So standard error of the difference between the two proportions. Faster line versus regular checkout. And here you have the square root. Square root will give you the standard deviation. In the square root, you have the variance, estimated variance. The 0.118, that is a proportion. Proportion people who pay with checks in this sample times 1 minus P1. That is the other side, the other proportion, the other people who pay with other means of payment. You divide it by the number of people, divided by 85. That's the number of people in your sample. And then you add the estimate from sample 2. For sample 2, you have 96 people. These are the regular checkout. And the proportion who paid with checks is 40.2%. And the percentage of people who paid with other means of payment, not checks, is 59.8. And you add them together, take the square root, you get the standard deviation. Standard error, the estimated standard deviation, 0.0619. And now you need you have all the information you need for getting your margin of error. The margin of error here, 1.96 standard deviations, 1.96 times the standard deviation. This will give you the raw score, the raw proportion, 0.121. This is 1.96 times the standard deviations. And your estimate of a population difference is negative 0.284. That's the difference between the two proportions of people paying tax. The standard error is positive and negative 0.121. Now you have the confidence intervals. Your conclusion, the manager can be 95% confident. Got to remember this by rote memory. This is confidence level. The manager can be 95% confident that the true proportion of all customers passing through the fast checkout line who pay with check is between 0.163, that's 16.3%, and 0.405, that's 40.5%, lower than the true proportion going through the regular checkout line paying for checks. This is a 95% confidence interval. You can get the confidence intervals and you can get the hypothesis testing. Confidence intervals is different from hypothesis testing. Let's look at the hypothesis testing. Well, in a random sample for 1,500 First Nation children, give me a second. So, yeah, you have a sample of 1,500 First Nation kids in Canada. 162 were in child welfare care. And in an independent random sample of 1,600 non-Aboriginal kids, only 23 were in child welfare care. Many people believe that a large proportion of indigenous children in government care is a humanitarian crisis. Do the data above give us significant evidence? Significant. What do we mean by significant? Statistically significant evidence. A greater proportion of First Nation kids in Canada are in child welfare care than the proportion of non-Aboriginal children in child welfare care. So your question is about the proportions between Aboriginal kids and non-Aboriginal kids in child care. Do these two proportions differ from each other in a significant way? Let's look at how we solve this problem. You have two parameters. One parameter is a proportion of kids who are First Nation children and who are in child welfare care. What is proportion? What is percentage? Is it 10%, 1%? And then the second proportion are the non-Aboriginal kids, non-First Nation kids who are also in child welfare. And when you're doing a hypothesis testing, you have a research hypothesis, we also call alternative hypothesis, and the null hypothesis. The null hypothesis is no difference prediction. You are predicting the proportions between the two populations on child welfare have no difference. They are equal to each other. When they are equal to each other, they have a zero difference. The difference between the two population proportions would be zero. That is a null hypothesis. Think about this. Are you trying to support the null hypothesis or reject the null hypothesis? In your research, you are trying to show evidence to reject the null hypothesis. You want to show the null hypothesis is not good, should be rejected. Another way to state the null hypothesis is that they are equal. You are trying to support the research hypothesis, also called the alternative hypothesis, H sub A. Sometimes you can write it H sub 1 versus H sub 0. Null hypothesis, research hypothesis. The research hypothesis says there's a difference. This difference is larger than 0. The difference between the two proportions larger than 0. And in more specifically, proportion 1, the proportion of First Nation kids in child welfare is larger than the proportion of kids among non-First Nation population in child welfare. You are trying to support the research hypothesis by rejecting the null hypothesis. You want to do a hypothesis testing. In this case, you are doing a z-test. A z-test, what does this mean? This means you are using the z-score, the z distribution. You are using the distribution of normal standard scores. That's a normal distribution. And before you can use a normal distribution, you need to check. So you need to check, see, the proportions. N1, so what's N1? N1, how many people did you N1 is 1,500. N2 is 1,600. Yeah, N1 times proportion for proportion, that's percentage people in childcare. That's you have to time 1,500 times the percentage. That's 89.55. And then the complement, N1 times N minus P, that is larger than 10. And then you check N2 times the proportion for 2, that's larger than 10. N2 times 1 minus P for 2 is larger than 10. So at least 10. The samples random and independent. The random, simple random sample, and they are independent from each other. And also it's less than 10% of the population. Your sample of 1,500 is less than 10% population of Aboriginals, and your sample of 1,600, sample 2, is less than 10% of the non-Aboriginal kids. And then you need to calculate the z-score, the z-score. Proportion 1 out of 1,500 Aboriginal kids, 162 are in childcare. That's 10%, a little bit over 10%, 0.108. How about non-Aboriginals? Non-Aboriginals out of 1,623 are in childcare. The percentage is like 1.4, way lower. And then the difference, observe a difference. Your observed difference between two samples is 0.094. That's 9.4%. This is 9.4% difference between the aboriginals and non-aboriginals. And you estimate the population standard deviation. Population standard deviation for the differences. Standard deviation you got to prove. So this one is a really special case in estimating standard deviations. Here, this is a p proportions. You can see you add the two samples. The two samples, sample one is 1500 and 1600, and then you also add the proportion of people in child welfare. For the 1500 sample, it's 162. For the 1600 sample, non-Aboriginals, number of kids in child welfare is 23. You add them together, you get a pooled proportion. Both populations pooled about 5%, 5.97, almost 6% of all kids are in child welfare. Now you use this proportion to estimate the difference. You use this proportion to estimate the difference in standard deviation. So this is pooled difference in proportions. 0. That's a 6%, 5.97% times the complement. And then this way you add up the proportions. It's 1 over 1500 versus 1 in 1600. These are the sample proportions. This way you get a standard deviation. You get the standard deviation. Once you get the standard deviation, you get the z-score. The z-score. So here you have a 0.094. Where does that come from? 0.094, that is a difference between the two proportions. Aboriginal kids, 10% on welfare. Non-Aboriginal kids like 1.4%. The difference is 9.4%. And what is the zero? The zero is according to the null hypothesis. According to the null hypothesis, there should be no difference, zero difference between the two proportions. They should be equal to each other. How far away you are from the zero? You want to know how many standard deviations is your observed difference from zero. The further away from zero, the more likely it's not zero. The more likely the real difference is non-zero. And the standard deviation you have estimated is 0.0852. And so your observed difference is 11 standard deviations. That's a lot. 11 standard deviations from zero. And what is the probability? The p-value, so z-score 11 standard deviations from zero, that's very small. See, if on my z table, do I even have 11 standard deviation? I don't. The largest the largest z-score I have is a 3.4 standard deviations. That's very extreme. Very small probability of having this kind of extreme scores. So the p-value is smaller than 0.001, smaller than 0.001, so it gives you 0.000. And then what's your conclusion? Your conclusion is in context. With this small p-value that is smaller than 0.05, there is sufficient evidence to reject the null hypothesis. In other words, there's sufficient evidence that the true proportion of First Nation children in Canada in welfare is greater than the non-Aboriginal kids. That's a conclusion you can draw. There's a significant evidence. Hypothesis testing. Okay, let's look at the quiz questions. We went through some of the quiz questions last time. We were doing question 6. And we did question 7. We did question 7 already, but let's review question 7. Question 7 is really interesting. This one is about extrasensory perception. Extrasensory perception is not real. It's like when you can see things that is normally invisible. You want to test. You want to, if anybody claim to have this ESP, extrasensory perception, you want to test. Is it true? And this test is asking the subjects to view the back of cards and identify whether the circle, square, star, or cross is on the front of the card. So you write, you kind of pen, you draw a circle or a square, star, or cross on the front of each card. And you want them to look at the back of the card. Can they see the signs on the front of the card by eyeballing the back? The P is proportion of correct answers. P is correct answers. And this may be viewed on the HO, the null hypothesis, P equals to 0.25. Where does that come from? Where does this P equals to 0.25 come from? That is 1 in 4. 1 in 4 equals to guessing. If you just guess, you should be right 25% of the times. It's one of the 4 answers. You can guess, is it square, circle, star, or cross? You get a correct answer 1 out of 4 times just by random guessing. That's null hypothesis. Null hypothesis says, well, the extrasensory sense are real. When you are right, you're just guessing. The alternative hypothesis says your hit rate is better than guessing. You do at least better than guessing, larger than 25%, larger than 1 in 4. And the subject recognized to have EPS when no hypothesis is rejected. When your evidence shows that the true proportion of correct answers by these guys is larger than 1 in 4, you can reject the null hypothesis. And you can recognize that, okay, the guy really has 特异功能. The guy really has extra sensory perception. What would be a type 2 error? Type 2 error. So type 2, what is a type 2 error? A type 2 error is different from type 1 error. What's the difference between type 1 versus type 2 error? Type 1 error is you reject the null hypothesis, but the null hypothesis is true. So you wrongly reject the null hypothesis. You mistakenly reject the null hypothesis when the null hypothesis is true. In this case, the null hypothesis says you're just guessing. Your heat rate is no different from guessing. And when this null hypothesis is true, you falsely or mistakenly reject it. That's a type 1 error. Type 1 error in this case would be when this guy has no special ability. When this guy has no special extrasensory perception abilities, you mistakenly believe that he has it. That's his type 1 error. And type 2 error is when the null hypothesis is false. When this guy does have some kind of a special ability, you don't reject the null hypothesis. You deny that he has special ability. So which one matches type 2 error? Correct. So let's go through this one by one. Correctly recognizing someone has special ability. Is that an error? No, this one's not an error. So it's not an error. We don't choose this one. How about this one? You mistakenly think someone has special ability. This one is you mistakenly believe this guy has a special ability. That is type 1 error. This one is that you reject the null hypothesis, but the null hypothesis is true. That's a type 1 error. You don't choose this one. How about C? Not recognizing that someone really has a special power. Not recognizing that someone really has a special power. Is that a type 2 error? That sounds to be a type 2 error. So when somebody really has special power, that means the null hypothesis is false. Someone's doing better than guessing. And you don't recognize that. That is a type 2 error. D, correctly realizing, well, if it's correct, then it can't be an error. This one is eliminated right away. How about E? E doesn't make any sense. It's not related with type 2 error, type 1 error. Question C, let's see. Question 8, look at this one. A researcher believes that skin cancer on the head or neck occur most often on the left. Most often on the left side. Because this left side is where when you're driving, you have the sun, facing the sun. And you have a review of 565 cases of skin cancer. And you have 305 occur on the left. What is the resulting p-value? So the resulting p-value this is a p-value, the probability. The probability of having 305 out of 565 cases is on the left. What is the p-value? Resulting a p-value, and you see here, the p-value we can get. So first thing you want to calculate the p-value, the proportion 305 out of 565. Let's get this proportion. 305 divided by 565, 54%, 0.54. 0.54%. And what you are concerned about is the research hypothesis versus the null hypothesis. The null hypothesis, according to the null hypothesis, HO, the true proportion should be what? It's either on the left or on the right. When you get cancer, it's either on the right or on the left. The proportion should be 0.50, half the time. But your observation is not. Your observation is a little bit over 50%, 54%. And what's your true proportion? So here you want the z-score. And for the z-score is a difference between 54% and 50%. 50% is specified by the null hypothesis. You want to see how far away the 54%, how far away is that from 50%. And in all the options, you have this difference. You have this on top of the z-score deviation, so it doesn't make any difference. The differentiator is below the deviation sign, is a denominator. It's denominator. Which one is good denominator? In the denominator, you should have the estimated standard deviation, the estimated standard error, or the standard error. And then this standard error is based on the null hypothesis. So the null hypothesis is 50-50, 0.5. And here, this is one that gives you the right estimate. So it's 0.5 times 0.5 divided by 565. And look at what's different. What's the difference between A and B? B, you have the probability corresponding to this z-score timed by 2. What does that mean? That means you are having a two-tailed test. So you are dividing between the left and right half of the normal curve. In this case, should you have a one-tailed test or two-tailed test? And it depends on your hypothesis. In this case, the hypothesis is directional. You're saying the proportion should be larger than 0.5. You're proposing that on the left, since you're facing the sun, the left side is facing the sun, there should be larger than more than half 0.5 probability you get cancer on the left side. And you are making a directional prediction. So you have a one-tailed test. Is good answer. Yeah. For question 9, actually we did question 9 last time, right? Let's do it again. See. The internet usage between Middle Eastern, Latin America, and you have a random sample, 500 adults in the Middle East and 151 claimed to be regular internet users. Random sample of 1,000 adults in Latin America, 345 are regular users. What is the p-value? And in this case, you look at the research hypothesis and null hypothesis. I'm going to copy these ones. Here, the null hypothesis says the two proportions should be equal. The two proportions are equal. So you have a P1 minus P2 should be 0. The proportion of internet users in the Middle East and in Latin America should be equal to each other. So the difference should be 0. The difference should be 0. And according to your research hypothesis, the two proportions should be not equal. Not equal. Do you know which one is larger? See here, do we predict which one is larger? No, we don't know which one should be larger or smaller. They're just not equal. Just not equal to each other. We don't know which one is larger. In other words, we are making a non-directional prediction. When you're not making a non-directional prediction, you should do a two-tailed test. In other words, you are concerned about the two tails of the normal curve. On the left, on the right, you're both concerned. So you want to, the p-value should be times 2. Get rid of, you eliminate all the options that doesn't have the two in there. And now you want to estimate the z-score, the critical value for the z-score. What are the z-score critical value? So the z-score, you have the observed difference. Your observed difference is, you observe the difference for the first sample, 500 adults in Middle East. And out of 500, you have 151 out of 500. Internet users, these are regular users. So 151 over 500, that is 0.305. And then you get you subtract. That's in random 500, yeah, you have a 1,000 in Latin America. 345 over 1,000. Let me separate these ones. So it's 0.345. So it's the difference is 0.305 minus 0.345. Seems Latin America have slightly more people, larger proportion of people who are internet users, regular internet users, about 4% difference. It is 4% difference are statistically significant. How far away is this 4% difference from zero difference? According to the null hypothesis, the two proportions don't differ from each other. In the two populations, you have the same proportion of people who are regular internet users. Your two samples show a slight difference. The two samples show a 4% difference. And your question is, how far away is this 4% difference from zero? How many standard deviations? How many standard deviations is it from zero? And you want the z-score. Standard deviations. How many standard deviations from zero? The key information you miss is a standard error, standard deviation. You need to estimate the standard deviation. And this really go back to the sample we just look at here. So here you need to pull the sample. You really need to pull the sample together in estimating the standard deviation. First, you need to combine the proportions. You need to combine the proportions. You need to add the two samples. You need to combine the two samples. And then you need to combine the proportion, the people who you are interested in the two samples and get the combined proportion. Let's see here. So first, let's combine the two proportions. Proportion estimate for the combined, you have C. This one should be a subscript. For the combined proportions, in the denominator, what are the samples? The samples research, no, you got the wrong place. This is wrong place, wrong question. Here, one sample you had 500 people from the Middle East. And then you have people of 1,000 from South America. And how many people you have in total for regular internet users? For Middle Eastern people, 151 internet users, and for Latin America, 345 internet users, regular internet users. And these are the proportions combined. Let's see here, got that. 151 plus 345. Oh no, 151 plus 345. That is a 496. 496 in total out of 1500 divided by 1500. That is 3306. 0.3307. Yeah, so that's a proportion of internet users. And then what do you do with that? And once you get pooled proportion, you can estimate the difference, the standard deviation of the difference scores. And here you have the p proportion times 1 minus the proportion, the complement. And then you times the proportions, combined proportions of the samples here. The proportion is like 0.33, 0.33. 0.33, the complement. If we want to go 2 decimal points, one minus this guy is 1 minus 0.33. So that is going to be 0.67. Yeah, so you want to 0.331, that's 3 decimal points. This term seems to be good. You have a 0.331 times 0.669 times 500, 1 in 500, and then 1 in 1000. This seems to be good, except you need two-tailed. Yeah, so D is good answer. D gave you the correct estimate. Good. So that's question 9. The greater the difference between the null hypothesis claim and the true value of proportion parameter. So the difference, the bigger the difference between the null hypothesis claim and the true value of the parameter. Yeah, which one is good? It's A, B, C, D, E. A, B. Look at this one. Well, fill out the blanks. Null hypothesis. The null hypothesis basically says there's no difference, no difference. And if the null hypothesis really has a big difference from the population parameter, it is good. Smaller the risk for type 2 error. What is type 2 error? Type 2 error says when there's a indeed a difference. When the null hypothesis is not true, you don't reject it. You fail to reject the null hypothesis, but the null hypothesis is not true. That's a type 2 error. And there's something wrong with this statement. When there's a smaller risk for making type 2 error, there's a greater power. The power, what the meaning of the power of a test is, the test will allow you to reject the null hypothesis. When the null hypothesis is false, when the null hypothesis is not true, the test allows you to reject the null hypothesis correctly. That is the power. The larger the power, the smaller the possibility of a type 2 error. In other words, the smaller the risk of making a type 2 error, the bigger the power. So this one's gone. This one's not good. How about B? The smaller the risk type 2 error and the greater the power. This statement is not wrong. This statement is good. This statement is true. But does this apply to the question? Question says you have the greater the difference between the null hypothesis and the true value population parameter. If the true population parameter is really big difference from the null hypothesis, does this allow you to have a smaller risk for type 2 error? Yeah, this one's good. Yeah. Let's look at C. This one's good answer. The greater the risk of type 2 error, the smaller the power. And this one seems to be, yeah, the greater the, right. This one's not wrong. This one's good. This statement is good, but it does not apply to the question. The greater the risk of type 2 error, and the greater the power. This one has the same problem as A. The greater the risk of type 2 error, the smaller the power. The greater the probability of no change. No, this one doesn't make any sense. So this one's gone. All right, let's look at the free response questions. Net neutrality is the idea that all internet traffic should be treated equally. That is, no internet service provider should have a power to favor one source over another by blocking or paid prioritization. Online survey respondents basically you have a sample of 155,612 internet users. Report 93% favor net neutrality with margin of error of 0.1. Actually, I don't even care about what neutrality is. I don't care about what net neutrality is. I only care about the sample. The sample's here, and The proportions 93% favor this idea, and the margin of error is 0.1. The question is, number one, what is a 93% statistical? Is 93% a statistical or parameter? Is it a statistical parameter? This is a statistic. A statistic is a description of the sample. You get this 93% from your sample. Out of your 155,612 people, you surveyed 93% of them favor the neutrality idea. That's a statistic. A parameter is about a population. Your population is way larger than the 155,612 people you surveyed. It's millions, billions of internet users. And a parameter is a description of the population. It's a value on the population. This is a statistic. Let's see. B, without doing actual calculation, explain why the margin of error is so small. Why you have a small margin of error? The margin of error is really small. You don't have to do the population. Well, what kind of a factor was influence margin of error? Because you have a large sample size. Your sample size is really large. When your sample size is large, standard deviation is small. Margin of error is related with a standard deviation. The margin of error is related with a standard deviation. How many standard deviation is your margin of error away from the observed value? 155,000 people is very large sample size, and it will give you a small standard deviation. And then let's look at this one. How confident you should be that between 92.9 and 93.1% of all internet users favor net neutrality. You get these two numbers. To 29.9 versus 23.1. How do you do that? So basically, these are the two boundaries, two margin of errors, and you want to get the confidence level. You want to say how confident should you be, the confidence level. Let's do this. See here. 93. So the observed value, the proportion is 93%. 93%, see here. 92.9 0.9 minus 93 what is the proportion? That is 0.1%. And how about the other one? 93.1 minus 93%. That is 0.1%. How confident you are that you should be so between these two numbers of all internet users favor this kind of opinion, margin of error. So the margin of error is 0.1%. And how would you figure out the confidence level? How do you figure out the confidence level? For the confidence level, you need the z-score. You need the z-score. How do you get the z-score? Now, you need to make the estimate of the standard deviation. Standard deviation. You're going to need this one. You're going to need n, and you're going to need the proportion. So you need the standard error. How do we do the standard error? You need a square root sum, square root. How can I get a square root? Let's get a mathematics. Okay. Here. You can square root 93%, right? 0.93 times 1 minus 0.393. You want to divide it by n. That's going to be large n, 1, 5, 1, 5, 5, 6, 1, 2. Within the square root sum, let me do this one. Oh, that's going to be really a large number, really a small number, tiny number. Yes, let's get a square root sum. Square root of 9, oh no, 0.93 times 0.07 divided by 155,612. 155,612. Take square root. That is 0.006 for 7. Yeah. This should be one more 0. Yeah. So here, yeah, that's a standard error of the mean. And then you can calculate how far away is this margin for error from 0. Let's see, basically you see is the z-score, the critical z-score will be 0.1. 1% is 0.01 divided by 0.000647. That's how many standard deviations it is from the observation. 0.1 divided by 0.00065 basically. Yeah, that's 153. 153. That's 153 standard deviations away from the mean. That's really a big z-score, a huge z-score. So you can be really highly confident, almost 100%, more than 99% confident that you're going to get this kind of proportions. Let's look at this next question. Random sample of 500 new births in the United States. 41% were to unmarried women. Wow, that's a lot. Well, in the random sample, 400 new births in the United Kingdom, even more. Wow. 46% were born to unmarried women. Cognitive 95% confidence interval for the difference in proportion of new births to unmarried women in the US and UK. Let's see, United States. So here we have two proportions. Proportion 1 is going to be estimated. Proportion 2, I'm using the little hat because I'm trying to estimate. I don't know the true proportions. Proportion 1, proportion 2, this is a US, UK. Let's use US versus UK. US, UK. The US estimate is 41%, 41.2. Let's use 0.412. For UK, 0.465. Is there a difference between the two proportions? Cognitive 95 is difference in the proportion, and the proportional difference. Estimated difference here. What's wrong with this one? It's here. Oh, something wrong with my computer. I don't want this one. Difference. Oh, here it is. And the between US and UK, right? 0.412 minus 0.465. And that's negative 0.412 minus 0.465, negative 0.053, 5% difference. You want the confidence interval. You want the confidence interval for the difference of the proportions between US and UK. And how do you do that? 95% confidence interval. 95% would give you the critical value. Z critical value, Z score. What kind of Z score are you looking for? Positive and minus. You want 95%. 95%, that's divided between the two sides. Why do you care about the two sides? Confidence intervals are always two-tailed. You also get two boundary numbers. You can't do a one-tailed test on the confidence interval. So 95 divided by 2, you got 47.5. 47.5 on each side. And you look at the Z table. 47, 1 point. Yeah, here we have this one. 47.5, that's 1.96. 1.96. 1.96 standard deviations above or below the mean. And for your confidence interval, you want 1.96 standard deviations. You want 1.96 standard deviations above the mean and below the mean. Now the key, yeah. Okay, you got back again. Now the key thing is that you need the standard deviation estimate. You need the standard error. Standard error is your estimated standard deviation. Now here we go back to review a little bit about the sample we went through. Now you need the pooled estimate. You need the pooled estimate. First, you need to combine the samples. You need the two samples to combine together. How many people did you get from the UK? And how many people did you get from the United States? Combine them. And then you estimate the standard deviation for the different scores. Here, we need the proportion of combined sample. Proportion for combined sample. you still are estimating. Let's see. First, you combine the samples. For US, you have a 500. For UK, you have like see 400. So you have total 900 people. So out of US sample, 500 times 41%, 41% out of 500, 0.412 single moms, single mother. And out of the 400 people from UK, you have 0.465 single mothers. And what is the combined proportion? Combined proportion 500 times 0.412 plus 400 times 0.465 divided by altogether you have 90 people. No, 900, I mean 900 people. 43.56. That's a 0.43 point. That's 4356. About 43%. It's just somewhere in the middle. 41% for Americans, 46% for UK women are single moms, but they have a different sample sizes. If you combine the two samples, the proportion of single moms in both countries from these samples, 43.56%. And this one is the value you are using for estimating a standard error for the differences. Let's go back there again. The P, the proportion, the complement, and here you have the weights. Standard error, let's see, we got where can I find square root sum? And here you have P, that is 0.4356 times 1 minus 0.4356, and you time it with 1 over 500 plus 1 over 400. That'd be 0.4356 times, oh no, that's 0. Let me do this other ways. 1 minus 0.456. Oh no, that's the wrong one. 1 minus 0.435. 0.4356 times 0.4356. That is 0.246. And then you times it with times 1/500. Oh no. 1/500 plus 1/400. That is 0.0045. Oh, it's one more. 0. Let's get a square root. Square root 0.246 times 0.0045. 0.3327. All right, 0.3327. So that is a standard error. You estimate it for the proportion, for the differences in the proportions. Once you get the standard errors, you get the Z, the confidence, not anymore, yeah. So one standard deviation is 0.33. And the 95, you want basically 1.96 standard deviations. Let me double check my computation, make sure I do it right. 0. Let me double check this one. Yeah, well, I don't have time, so let's see. Basically, the confidence intervals. The lower boundary negative 1.96 standard deviations below the mean. You time it with 0. So negative 1.96 standard deviation below the mean 0.3327. That's negative 1.96 standard deviations. So it's negative 1.96 times 0.3327. That's a 0.3327. 0.619. 0.619%. That's a 60%. 60%. That's negative. And the positive 1.96 times 0.3327, that is positive 0.619. Yeah, this will be the boundaries for the confidence interval. The confidence interval is pretty wide, so it's really it could be either the US has a 60% less, or the UK has 60% less single moms. All right, yeah, so time is up, guys. Go through this. So we are almost finished. We are almost done with quiz 24. Now go over all these questions in quiz 24 by following the video. All right, I'm going to send you a link to the video probably today, later today, and also the link to the video from last time. I got to post it in the internet and send you the private links. Okay, have a good weekend, guys.
Have a good weekend. Thank you. Bye.
Bye.